Hey guys, I promised you just that I would finish a few more minutes about this connection between these linear transformations from Rn to Rm and the matrices, the m by n matrices that we can correspond with those linear transformations. It turns out this can be very helpful to us when we're studying geometry problems, when you have transformations that are things you can picture, such as from R2 to R2, or even in R3, we have some examples. And so I just wanted to show you kind of how that might look, just for a second. Let's suppose we have a transformation. We don't have a formula for it yet, but let's imagine that it reflects points across the line y equals x. All right? So here's kind of a picture of what that might look like. You have a point AB, and the transformation comes along and it reflects the point to the point BA, which is on the opposite side of the line y equals x. So this is just T of AB, and it equals BA, right? So, of course there will be a 2 by 2 matrix that corresponds to this, right? I don't really know for sure yet what it is. Let's just put down some numbers, A, B, C, D. But some 2 by 2 matrix can be viewed as the tool that does this transformation. Okay? So, for example, if we take if we take this matrix, let me just take a specific example here. I think this will show you how we can find the matrix. If we take the matrix A, B, C, D, and we know that if we took an input, let's say the point 1, 0, when I reflect the point 1, 0 across the line y equals x, it's going to become the point 0, 1. Okay? And if I do the matrix calculation here, I see that the vector that I get on the left is just the vector A and C. So I'm just using matrix multiplication to figure that out. The conclusion that I'm going to reach down here is that the two entries have to agree. A has to be 0 and C has to be 1. All right? Similarly, if I started with 0, 1, then after I reflect that across the line y equals x, I should get 1, 0. And when I do this calculation, I have 1, 0 on the right. On the left side, I have 0 plus b, which is b, and I have 0 plus d, which is d. So b has to equal 1, and d has to equal 0. Great. So my matrix is actually the matrix 0, 1, 1, 0, if I just put the numbers that I found here into this matrix. Okay? Now, for example, if you think about it for a second, if you were to, let's say, apply this transformation twice. Let's say you reflected a point across the line y equals x, and then you did it again. Well, what would that do what would that new transformation, which I guess we could call it t squared, what would that be? Well, if I apply the transformation twice, you might realize that what's going to happen is that you're going to start at the point AB, transform it to the point BA, and then it's going to get flipped back to the point AB again. In other words, we would expect that if we applied t squared of any point AB, that we would get AB again, right? And remember that under my correspondence that I showed you guys earlier today, composing this transformation with itself should be equivalent to multiplying the matrix by itself. And sure enough, you can check it out that if you take 0, 1, 1, 0, and you square it, you will in fact get the well-known identity matrix. This is the matrix that basically does nothing. If you apply the matrix 1, 0, 0, 1 to any point xy, well, you're just going to get xy back again. Okay, so that's one example. Now, another example would be maybe something like this. Let's suppose that I did a transformation. Draw a picture of it for you here. Let's suppose I took a transformation from R3 to R3. Okay? And let's imagine that the transformation takes the point x, y, z and just smashes it straight down perpendicular to the point x, y, 0. All right? So this is like a projection map. It's a projection function. Okay? So we would expect there to be a matrix that would be a 3 by 3 matrix that would effectively do this transformation for us. What we know, for example, is that basically the z-coordinate has to get lopped off. But if we think about what the matrix would be, let's say we put in these 9 numbers here. This is just one way to think about it. Okay? If we put any vector here, let's just say we put x, y, and z. Actually, let's take a specific one. Let's say we took, let's just try 1, 0, 0 for a minute. Okay? If we have 1, 0, 0, and we project it here, we're going to get 1, 0, 0 again. Right? So we know that our matrix should do that. And if you work this out, this is going to give you, when you do the calculation on the left, you're just going to get the first column of the matrix. Okay, so you're going to get an A, and then a D, and then a G, like that. Okay? So so 1, 0, 0, I'm sorry, this is not quite right, is it? This should be 1, 0, 0 goes to 1, 0, 0. This should have been a 1 right here. There we go. So A is equal to 1, D is equal to 0, and G is equal to 0. If you try this out with 0, 1, 0, you're going to find out that, well, I'll just show you here. 0, 1, 0 should get projected to 0, 1, 0, right? And if you calculate the product of this matrix multiplication here, right, you would get B, E, and H. So B is 0, E is 1, and H is 0. Okay? Now finally, if you plug in 0, 0, 1, so you put a 1 for the z value, well then you're going to get 0, 0, 0 out of this, and here you're going to get C, F, and I, all of which have to now be 0. C is 0, F is 0, and I is 0. So your matrix is the matrix 1, 0, 0. The only ones are basically the A and the E. So there's your transformation. Okay? Let's say you wonder what happens if you do the transformation twice. Okay? Well, maybe instead of thinking about it geometrically, I can just use the matrix to do it. If you square this matrix out using the regular process of matrix multiplication, what you're going to find out is that A squared is the same as A. What that really means is that once you've applied the transformation once, then the second time you apply it, nothing new happens. And once you realize that from the algebra, from the matrix side of things, it makes so much sense in terms of the picture. Once you smash this point down to the xy plane, it can't be smashed any further. It's already been completely flattened into this xy plane here. So if you project again, if you apply the transformation again, so that you're really doing t squared, well, you just end up with this same point. It projects to it the second time, it just projects to itself. Okay? So the matrix informs us. By having the matrix here, it tells us, even without thinking about the geometry, what's going to happen, which is that this point gets flattened originally with the first transformation, and then when you apply it again, it just stays put. No surprise with any of this. I just wanted to share it with you. So there's some geometry that you can combine with the matrices here and the transformations. And this should also hopefully be helpful to you for the next homework assignment. Okay, hope you guys enjoyed it. Let me know if there are any questions. Thanks a lot.